Yeah, so tell me if you can hear my voice in the stream. Damn, bro, why is it lagging? What?
Okay. Send
Hey,
the link in summer school group at least.
yeah, yeah, I sent it in our group, the one with all chords. Oh, I forgot to link my tab. Okay. Hello, bro, can you go to the stream?
Hmm?
Can you go to the stream
Yeah,
and see
where?
if my voice works?
Yeah, wait. Like I'm trying to find where the bloody. Okay, got
Um,
it. Turn off Bluetooth from here. Increase the volume. Yeah, your voice is coming.
all right, cool. Fine, so I'll do this.
Wait, hey, use Spotlight view only, bro. Like it
Yeah,
will become
yeah,
even
I'll,
bigger.
I'll do that, I'll do that, I'll do that. Chill.
Mark your attendance again.
அது ரெண்டாவது வாட்டி பண்ணுவாங்க. Yeah, then we need that BRB photo. Oh, oh, you can't see my desktop. Haha, I hid it. Okay. Uh, that's default shit, bro. You just like enable it and it'll do it on its own. You don't have to do anything. Okay, this will be right back should be there now. Day. What 2:30 to 3:30? I said it'll start at 1. Yeah, correct. I typed. Okay. Um, சொல்றேன். One last thing I need to do, which is to connect my tab. I mean, decent only, man. All right. Okay. So if I do this, yes. Okay. Doesn't. Okay, bro. When we switch, no, take like 5 seconds after I'm done before you start.
Okay.
So yeah, I'll just like resize the frame so that it fits your screen properly. All right. Fine. So I think we'll put link public. I mean not public, but yeah. Okay. I'm sending the. Hello,
Uh,
all.
yeah, send. I mute.
Yeah, I'll also muting this.
Wait, why are you muting in stream, bro? Open in stream. Fine, for now then. Okay. Whatever. Look. I'm pinging at. I'm pinging.
Okay, cool. Hello, guys. Is this can you guys hear me? The setup today is a bit different from what we've been doing. So, okay, cool. So, I guess you guys can hear me. So, let's get started. Cool. So, yeah. So, as you guys already know, today's this discussion is going to be about some basics of vector graphics and stuff. So, exciting stuff, right? So, let's start by asking a question, which is, or rather, you guys would have interacted with images and stuff a lot in your life, right? Like in school and all to make PPTs. I mean, even in college, everywhere in life, you'd want to make PPTs, or sometimes when you want to put a background wallpaper for your laptop, you would like Google wallpapers, right? And many times while doing that, you will search whatever, and then 4K or whatever 8K or something. Similarly, to make this slide, I searched for a forest trail background 4K. So, like, why do we want something in 4K? Why do we want something in good quality? The reason is because when we try to zoom and make, not zoom, when we scale it and make the thing bigger, if the size of each pixel in the image is small, then it will be like even if you make the image relatively large, your eyes won't be able to distinguish between two pixels, right? That's the reason why we want to have 4K, 8K and stuff. And this is pretty good because now when you make things bigger, it is resistant to scaling. I mean, resistant to blurring or pixelating. So this seems like a nice solution. Whenever you want to make things relatively large, you can make it 4K, 8K, some high image quality, and you'll be set. So, but there's a small problem, which is which is that 4K, which is that images are not the only format of pictorial data we interact with every day. So for an example, let's take font size, right? When we take fonts, we resize fonts a lot. We'll make fonts 11. Google Doc, I think, defaults to 11 as the font size. When you're making a PowerPoint or something like we made this one, some of the fonts here are at 150 size. So imagine if every font is like in 4K quality, then the quality will be good. But think about the file size. It'll be completely cooked. It'll be too much. So and like if you take a single font, it has like 26 letters in lowercase and then 26 more in uppercase, and then you have like 10 numbers and then all the brackets, apostrophe, hyphen, underscore, equal to, plus, minus, all these characters. If each of those are 4K images, then your entire SSD will be filled with only font size. It'll be too much. So an interesting question arises, which is how can we deal with this? How can we make an image which is resistant to scaling? I mean, that seems like a very insane question to ask. I mean, how are you going to do that? It's all represented in pixels, right? So, okay, uh, let's take a let's like stop restricting ourselves too much. So we already know how pixels work. We know that it's limited, but let's just say that this world is in like crazy and you can get whatever you want. Then something nice that you could do is this adaptive gridding. And what I mean by adaptive gridding is, let's say that you want to draw a circle, then you'll start, if your picture size is relatively small, then you'll start with this like bottom left situation, right? So let's say it's like a really low, poor quality, only 3 by 3 is the dimension of that. So you'll start with this relatively like small grid. And as you make the size of the picture larger and larger, what you can do is you can tell the computer, hey, fill up the pixels, like whatever the missing pixels are, fill it up with a circle. And if they make it even bigger, like the one in the extreme right, then you can again fill in more extra pixels, right? But I mean, I don't have to tell you what the problem with this is. It is just how are you going to fill it, right? Like you need to store that data somewhere. And that is the problem we are even trying to solve. We want to not store the data in the first place. Like We want to start with a limited thing and use only that. So adaptive gridding seems like a good starting point in the in a sort of philosophical sense, right? Like you start with a small image, and when you make the image slightly bigger, you re-render the whole thing. But the only problem with this re-rendering step is, how do we re-render? That only we don't know. The computer doesn't have the instruction set to do the re-rendering. That is the problem. So how do you think we can tackle this? Yeah, so someone has put a question, how do you know it's supposed to be a circle or a square? Exactly. We know, as humans, we know whether it's a circle or a square. When I was making the slide, I knew I wanted to draw a circle, and I have, as a human, I'm like relatively smart, I guess. And so, like, I used my own intuition for how a circle is supposed to look to draw this. But yeah, exactly. A computer doesn't know what a circle or a square is. It doesn't know what a straight line is. It doesn't know anything. So you cannot expect a computer to draw this by itself, like fill in the pixels by itself. You need to give an instruction set. So that's the idea. And since this is like a mathematically driven thing, you can probably guess that a good sort of idea for an instruction set is to use a function. We can use something like y equal to f of x to draw the shape, right? So now our new strategy would be something like this. You will start with, so your computer program will no longer store the pixel values, and like it will not store the, it will not store something like the third row fourth pixel should be red, then the fifth row sixth this thing should be white. It will not store this information. It will instead store f of x, okay, which is a function. And the way we will draw the images, let's say the function ranges from 0 to 10, okay, then what we'll do is we will input into the function all the x values from 0 to 10, and then the function, which is our program, will generate all the y values. Then you can take x comma y as the image that you're trying to draw as you're drawing itself, right? So okay, that's a small caveat, which is kind of like the feature of the whole situation actually, which is that for a computer you cannot really supply all the values from 0 to 10. That is just crazy. You have to have some discrete step size. What I mean by that is, you can say something like enter every value at an interval of zero point 0.1. So then you will, all your x values would be 0, then 0 0.1, 0 0.2, 0 0.3, so on till 10. So that's why I've indexed it as xi. So there it's like an index thing, it's a discrete set of values. Okay. So then it will generate the corresponding yi. Then xi comma yi will form your like set of all your points. Then you plot all the points to get the shape that you want. And the amazing thing is, if you make the shape, if you make the size of the picture bigger, all you have to do is make your step size smaller, right? So instead of having, we started with zero point 0.1, if you make it doubly big, then make the step size half. Then you'll again, like now your computer knows how to draw the missing bits because it has f of x, right? So this is the like big idea of thinking about using a function in the first place, which is, I mean, in a certain sense, a function has like infinite information stored in it, right? Like you can put any x value to give the y value. That's kind of insane. So, and that's what we're exploiting to draw this. Okay. Now, if we just sort of take this new feature or new system we have created, it has like completely solved the scaling problem, which is basically, how do you solve it? If you make the image bigger, take a smaller step size for x, and then you're done. But by definition of a function can't loop. Like the thing you're plotting is basically y equal to f of x. And you guys already know that based on the definition of a function, you can't loop. For a single x value, you can only have a y value, right? Like you might have even studied this vertical line test in JE and stuff. If you draw a vertical line and it cuts the curve at 2 points, then it's not a function, right? So that's the problem. You can't draw any loops with this. And if you guys like saw the Batman logo which I sent in the group, you can clearly see there is some kind of looping there. For the same x value, there are two y values. So that we might want to draw something like that. And we can't use a function like y equal to f of x for this. So what could we possibly do? Let's try to analyze. Let's think about this. If you think about what we're basically doing, this xi is really doing two things, right? It is acting as the parameter. So that is what you supply into your program to generate yi. So that is one thing it is doing. It is so that's and then another thing that it is doing is it is also part of the point you're plotting. So it is both a parameter and it's part of the point you're plotting, right? So so that raises two questions for us, or not two questions. It's like a question and a follow-up, which is, does xi have to do both of these things? Like, does it have to be a parameter and does it also have to be part of the point you're plotting? Or can we like maybe split it in two parts? And let's just say that the answer is yes. We can like split into two parts. Xi doesn't have to do both of these things. Then what will basically happen? Your output will be only yi. The thing you're plotting will be only yi, and yi is a number. Why is yi a number? Because this function is from R to R, right? So that's what I've defined in the previous slide. F is a function from reals to reals. So yi is a number. And if you want to plot a number, it will go on the number line. And then what 1D drawing will you have? You'll have a line. So that raises the second question, which if you decide that xi is not going to do both of the things, then how can we get a point to draw on the plane? Like it will only be on the number line. So this is the like dilemma that we are in right now. And if you think about what I just said, the whole problem is that yi is a number. The output of the function is a number. It is from reals. So that raises a curious idea, which is, does the output of the function have to be in R1? So what if the output is not R1? What if the output is actually R squared? So you'll be inputting scalar values, you'll be inputting xi values, and you'll be getting yi values. But then the yi values will be from R squared, meaning yi itself is a point. So it itself will have one x coordinate and y coordinate. That xy is not related to xi yi. I hope you guys understand that. The yi itself is a whole point on itself, and then now you can plot yi on a plane, right? So this is quite a good idea. You now have a single parameter, which is let's call it t. Okay, so you guys would have done like at square comma 2at and stuff in JE. So we'll continue the same uh, what do you call convention. So we'll call t as the parameter. So t will be some scalar real number. You will input that into the function, and the output of the function will be in r squared, which will be a point. So now what that will do is it will. So this is going to be quite fun. So yeah, the solution is to make the range r squared. So that will basically, our input will be a number, a scalar number, and the output will be a point. Okay. And what that will do to the functions that we are used to is this. Usually we see things like y is equal to mx plus c, that is a straight line, right? And y is equal to ax square plus bx plus c, that's the quadratic that we're used to. And I mean in J we have generalized that a bit. We will say things like ax square plus by square 2hxy and stuff. But actually that whole 2hxy blah 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 is summarized in this thing which I've written in yellow. R vector is m vector t plus c vector is a line, and the a vector t square plus b vector t plus c vector is a quadratic curve. But now no longer the parameter is not your x coordinate anymore. It is just t, and the thing you're plotting will be the output. T will not be involved in the output. By output I mean the point you're plotting. T will not be involved in that. So now let's say you decide to use a quadratic or something. Then if you want that quadratic to pass through some set of points, you need to not only give those points, you also need to now give the t value at which it should happen. So do you see how now we can start to make loops? You can like tell the function to pass through the same point twice for different t values. That is completely legal with a function, right? Like you could have f of 1 as 5 and f of 3 as 5. That is like legal for a function. So that is the idea of parametric functions. So let me just, yeah, so let me now exit this. Let's go to Desmos. And so let's start with a simple thing. Let's say y is equal to mx plus c. Uh, so hopefully this is visible. Yeah, so I think, yeah, so I think this is visible, right? Yeah. So this is what we're used to drawing. Y is equal to mx plus c. But now let's try something fun. Let's say, let's take a point. So let me call the point P. Let's take the point P to be 1 comma 1. And let's take Q. We'll take some other point. Let's say 2 comma 3. Okay, so we have 2 points. And now how I will draw the new curve is I will say P into T plus Q. So it's like a point into the parameter plus Q. And yeah, so as you can see, it is generating a line here. And by default, Desmos is ranging the parameter t to go from 0 to 1. If I change this from like, let's say minus 100 to 100, yeah, you kind of get the whole line, right? And I mean, if I zoom out enough, you'll see the line end. But yeah, in principle, you can get the whole line with this parameter. Cool. So this is very nice. I mean, if I move this, it does some interesting stuff. It seems very unintuitive though, right? Like, okay, I guess it's kind of intuitive. Not, no, not really. I don't know what this is doing. Uh, like, wouldn't it be a lot more intuitive if, like at t, let's just put this from 0 to t, 0 to 1. So at 0, the function is giving us q, right? And at 1, it is giving us p plus q, which is the sum of these 2 points. The sum of these two vectors is this point. So that's where the line ends. It would be a lot more intuitive if it started at q and then ended at p. That would make a lot more sense. And not lot more sense, meaning it would be a lot more intuitive. That's all I'm saying. You draw a line segment from p and q. It would have that meaning. So how can we achieve that? Uh, yeah, exactly. It's like the generalized vector form of a line in 3D. Yeah. So that's exactly, I was going to mention that and you mentioned it. So that's pretty nice. So pt plus q. Now, when I put t is equal to 1, I want this q component thingy to become 0. So what I'll do is I'll multiply it with 1 minus t. So can you see the effect that this has? This now is just a line segment from p to q. So now this is like, I would say this is at least, even if you had some random intuition for the previous thing which we had, you can't deny that this is like 15 times, billion times more intuitive than that. It makes sense. Like you start here and then you end here. And t plus 1 minus t is 1, right? And t is ranging from 0 to 1. So each of the coefficients for our points, t and 1 minus t, you can think of as some kind of weight. And the sum of the weights is 1. So essentially what we're doing here is taking a weighted average, a linear weighted average between p and q, and that generates a straight line. So pretty intuitive, well and good. Now, uh, so now let us try to add one more point. So let's put r also. Let me just put 1 comma 1. Now we can draw a quadratic. So we will say pt squared plus qt plus r. And again, so nicely you get a quadratic. And t is ranging from 0 to 1. Okay. This is section form. Yep, this is section formula. Yeah. Uh, if you put t0 into this quadratic, you will get r as the output, right? So that is the starting blue color point here. And if you put 1, you will get p plus q plus r, which is the sum of these 3 points. That's the end. And again, like last time, it was pretty intuitive to have it end at that point, right? Like you start at p and end at r. That makes intuitive sense. And the way we achieved that was we simply multiplied that with 1 minus t. So let's just do that here as well. So if I do 1 minus t, it doesn't work. Right. The reason for that is this q also is there. Right. We need this q also to become 0. So we multiply q also with 1 minus t. Ah. So now you can see nicely it is like between the two endpoints now, and it doesn't pass through q. That is true, but at least its effect is kind of intuitive, right? Like if I pull this out, it stretches it's like a bow and arrow kind of you, and then you shoot. Maybe this is how they make bow vectors. So might as well, right? So pretty nice. So that's nice intuitive meaning. You pull it up, it goes up, down, it comes down. So this is nice. Um, So let's just play around with this. Let's see what we can do. So if let's say I keep this here and I keep this here and I keep R at the origin. And one thing which I want to see is something which would be useful to draw vector graphics is translational invariance or translational equivalence. So what I mean by that is if I displace all of the 3 points by the same vector, I want the whole shape to be displaced by the same vector. So let me just define a point. Let's call it V. Initially, I'll make it 0. And to all my 3 points, I'll add V. Okay. So now you can't see anything because V is 0. Uh, so what I'll do is let's make this V 0 comma D and then I'll add D as a slider. Yeah. So now as I move D, yeah. So let me zoom out of this. Yeah. So this is good. So you can see how it is maintaining translational invariance or equivalence. So even if I add a vector v to all the points, the shape doesn't change. The entire shape shifts by v, right? So that's pretty nice. Okay. What about some kind of symmetry? So let me just remove all of these things. Okay. So if I come here, uh, we would expect that this minimum is just above this black point, right? It should be above Q. That's kind of, this would be kind of like the vertex of the parabola, right? But it's instead off to the side. And if I swap these 2 points, so I put this, where was it? I think it was here. Yeah. So you would, it does what you expect, right? It goes to the other side. It's not symmetric in P and R. Like it's not symmetric in the endpoints. And why would we want symmetry in the endpoints? It is basically if instead of letting t go from 0 to 1, if you want to go the other way, like if you want to go in the backward direction, you replace t with 1 minus t, then you would want the shape to not change. You would want the shape to stay the same. So let's say, for example, you want to maybe draw a car that goes from this purple point to the blue point, and then you want it to come back. Then you might want to reverse the direction by flipping t to 1 minus t. But what that will do with the situation we have right now is that it will flip the whole shape. So that's not good, right? We want it to be symmetric. And if you come and inspect our equation carefully, you can see why the problem is occurring, right? If you replace t with 1 minus t, this q term will not change. It will just be what it is. But then this will become 1 minus t squared, but this will become t. The coefficient for r will be a linear, it won't be a quadratic. We want it to be t squared. So let's square this. And upon squaring it, now it is nice and symmetric. It looks very good also. And if I do this, it doesn't change, right? So this is nice. Now let me do one thing. Uh, Let me just switch to my tab to talk a bit about something. So yeah. So so far what we have had is our quadratic R is basically P vector t squared plus q vector t into 1 minus t plus r vector 1 minus t squared, right? So in a sense, you can kind of think about it like a dot product. So you take p vector, comma q vector, comma r vector, and then you dot it with t squared, t1 minus t, 1 minus t squared, right? And for those who know how matrix multiplication works, this is basically a matrix product, right? So I'm not going to write that matrix product right now. We will see it later in the session. But yeah, this can essentially be written as a matrix product. But okay, so this thing over here, this fellow is what we will call the basis for our the basis parameters. The parameter is t. These are like the basis set that makes the quadratic curve. And if you remember, we wanted translational invariance. We had translational or as a translational equivalence, I guess is a better way of saying it. But we had that when we did not square this, because then t squared plus t into 1 minus t plus 1 minus t, this fellow will add up to 1 if I don't square it. But then for the symmetry's sake, we squared it. So now this is no longer equal to 1, which means that this will no longer be translationally invariant. So if I go back to the graph, uh, yeah, so if I go back to this graph and I do what I did before, so I'll add another v, okay. So I say 0, comma 0 plus v plus v plus v, and again I'll do this. Yeah, so now you can see, let me just zoom out. As I move D, can you see how the entire shape is changing? Right? And it's not just that it's scaling also, it's getting squished as well. So here it's almost like a straight line at this point, and then it bends downwards. We don't want that. We want it to be translationally equivalent. So the way we can achieve that is by forcing this summation to be 1. And how we do that is a very, I'm just going to give you the answer and then I'll wait for maybe a few minutes, or not a few minutes, few seconds, and you guys can tell me what it looks like. Okay. So the answer is you multiply this with 2. Now t square plus 2t 1 minus t squared will add up to 1. Now, does this look like anything you guys have seen before? T squared 2 into t into 1 minus t squared. I'll give you guys like 5 seconds. The stream lags for me, so I can't see the chat exactly. Yeah, it's a perfect square. Nice. Or in a more general way of saying it, this thing is a binomial expansion, right? We are taking 1 and we're binomial expanding 1. So you take 1, uh, you write it as 1 minus t plus t, and then you square this. And this produces a basis set where all the terms are quadratic. That's good, right? If any term becomes cubic, then the shape you get is no longer a quadratic. So this is now all the terms give you a quadratic, and by definition of how a binomial sum is, they will all add up to 1. So now we get an interesting idea, which is that if I want to draw, let's say, a cubic curve, then all I have to do is I will binomial expand 1 minus t plus t the whole cube, and then I will use that as the coefficients, as the basis. So let me just, as a small example, oh, by the way, if I put 2 here, this will now not change shape. So yeah, uh, okay. Mm, let's just do a cubic as an example. So let me take S as again some point, so 2 comma 5. Let's just see how it looks and then we will go to the next part. So pt cube plus q, and then we need the next term of the binomial expansion, which is 3t squared 1 minus t, and then we need the next term, which is 3t 1 minus t squared, and then the last term will be pqrs is what I called it, so 1 minus t cubed. Yeah, let me hide the quadratic. Let me also just remove this p. For now we don't need it, so let's do that. Yeah, so now you have, this is the cubic, and again, just like because of the way we have structured this, it will start at p, it will end at s, and yeah, this is now a cubic curve. It doesn't look like a cubic, it definitely does not look like a cubic. Like, it looks like some, maybe an exponential. We can fool people, we can do it like this. Maybe move this. Yeah, this is now 1 by x. This is now a reciprocal function. This does not, basically the point I'm trying to make is, this doesn't look like a cubic anymore, because it's not a cubic in x, it is a cubic in t. That is the key thing that you have to keep in mind now. The parameter has changed. The parameter is some t, and t is not part of the plot we are making. Okay, and these two are like the start and end points. These two are like, the curve doesn't pass through these 2 points, but it gives you some kind of intuitive control over the curve, right? Uh, why is there translational invariance if the basis adds up to 1? Yeah, so I'll explain that once. Yeah, I forgot to talk about that. I'll come to that in a second. So as I was saying, the curve doesn't pass through these 2 control points, but at least their effect is kind of intuitive. Like, if I move the blue point this way, the curve moves that way. If I move the black point in any direction, the curve moves that way. And now further, if I want to make a loop, what I'll do is I'll swap the order of these 2 points. Now can you see we have a curve now with a single function. So this is the sort of brilliance that you can do with a parametric function now. It is a function from R to R squared. Whatever shape you want to draw, put it as the range of the function. And then you put your parameter to go from 0 to 1 or whatever range you have, and then it will draw the whole shape. Okay. So before we go to the thing, let's quickly talk about this invariance thing. So let me start off with just a quadratic. So let's take P. Uh, let's just say that this fellow's coefficient is some f of t. Okay, some quadratic in t. Then it is q into some other function in t, and then r into f g. Let's take h. So let's say this is our curve, and then let's say every point we shift it by v. So p becomes p plus v, q becomes q plus v, r becomes r plus v, right? So then what, so this is my r original vector. What will my r new vector be? Okay, this is bad notation by me. I'm using r here and here, but hopefully you guys get the point. So let us now replace p vector with p plus v, q with q plus v, r with r plus v. So what will we get? We'll get p plus v into f plus q plus v into g plus r plus v into h, right? And let me, yeah. Then if I factorize this, we'll get pf plus qg plus rh. So h of t, g of t, f of t. This is like the r original that we had. Then we will add v vector times f plus g plus h. So now what we need is f plus g plus h must add up to 1. And if we make f and fgh terms of a binomial expansion, by its own, by its very definition, the three will add up to 1. So that's the big idea of this parametric thing. And uh, and now hopefully you guys can see how we can get, like, draw a whole variety of stuff using these things. So yeah, and now just like, let's, oh, one last thing of terminology which I want to uh, introduce to you guys is this thing called lerping. Okay, it's linear interpolation. So if I want to draw a straight line, let's think from this binomial expansion framework. Okay, so if I want an n degree curve, I will take 1 minus t plus t power n. That will give me all the basis terms. I'll multiply it by the points and I'll get an n degree parametric. So now in that frame, if I want to draw a line that is a degree 1 curve, so I will binomial expand 1 minus t plus t power 1, which is just 1 minus t plus t. So that's basically how we get the initial thing that we had. So tt plus q into 1 minus t, which is the straight line that connects p and q. Okay, this thing is called linear interpolation. Why? What is interpolation? Interpolation is basically drawing a function that passes through some points that you want. So now we have p and q. Those are the points that we want our function to pass through. And what is the function we are passing through those points? It's a line, which is a linear entity. So that's why this is called linear interpolation. Drawing a line through 2 points is linear interpolation. Then if we did the quadratic thing, and how will we do the quadratic thing? We'll binomially expand. So we'll get pt square plus 2qt into 1 minus t plus 1 minus t squared. Now this is quadratically interpolating between p and r, but it is not interpolating through q. So that's the thing that you have to keep in mind with quadratics. With a linear, it interpolated through all the points you put, but for a quadratic, it's not interpolating q. And if you remember with the cubic fellow, there were 2 points that it didn't pass through. So it interpolates again, like whatever Bezier you draw, it interpolates only from the start and end point. And that will become an important point later in the session today. Okay, so yeah, so I guess that's it for now. And yeah, as like it's given in the as RF has written in this thing, it's, we will shorten it as LERP. Okay, linear interpolation is LERP. So yeah, so that's it for my part. We will go to RF now. So by the way, are there any doubts or is it okay now? So I guess there are no doubts. Cool. So let's move on to Arav's part now. So yeah.
Hello, everyone. Am I audible? Hello. All right, then I will start. So, welcome to the fourth part now of this presentation. So, we will start looking at Bezier curves in their actual use in vector graphics. Right. So, now before we used linear interpolation, and using the linear interpolation, we were able to connect 2 points. Now we also saw, I think Kailash also showed you guys both the quadratic and the cubic Bezier curve. But I will show now one more method of actually arriving at this, because obviously we came through like kind of bit of guesswork by using these binomial type formulas. I'll show you a much more cleaner way to arrive at these um, equations. Now, what we have here is 3 points, right? One, two, and a third point, which we refer to as a control point, right? This is a quadratic Bezier curve, which I'm sure you guys have already seen. But let's look at a derivation of this, right? So to make a straight line, obviously we already use lerp just once. Think about this. Okay, suppose I take these 2 points, the first point here and another point here, and I do lerp between those, right? Same I will do for this point and this point, right? Now, when you linear interpolate a line, of course, there's a parameter, the parameter t, and t goes from 0 to 1. As t goes from 0 to 1, a point will travel from here to here, and the other point will travel from here to here, right? So if I show this slider, you can kind of see these green points, this green X and this green X. What happens now? I will connect these two X's with a different line, and on this line, I will again linear interpolate. So basically, I've linear interpolated 3 points to find two more points, and then the 2 points, I've interpolated them to find 1 point. And now magically what happens is that if I range t from 0 to 1, this star, I'll slow this down. This star you can see, which is formed only via linear interpolation. Literally, we have used 3 lines. This draws out the perfect quadratic Bezier curve, right? And in fact, I can move this around all I like, but the whole thing is defined exactly by linear interpolation. So that allows us to do basically whatever we want, right? Now, this obviously is a very good graphic, but let's talk about now we have looked at a few curves, but let's talk about actual use case. And the use case would be basically drawing images, drawing, let's say, like the Batman logo that Kailash sent in the group before. What will happen now is this is really difficult to manipulate. Sure, you have like 2 points, right? And it's interpolating the 2 points. You have only one control point, and that doesn't really allow for a lot of diversity, If I just remove that for a little bit, that doesn't really allow for a lot of different kinds of curves. You'll just see like this, right? If I wanted to draw a Batman logo, maybe I have to use hundreds of these curves because they're kind of primitive, right? So instead of just starting at 3 points, we will move to, right. Also, one more important point is, I think some of you may be familiar with degrees of freedom. Degrees of freedom is basically how many ways I can modify this shape. This basically has, if I have fixed the endpoints, to define this curve, I have only 1 point. Now, what that does is this. Suppose you look at this line and between these two lines and the red curve, you will see that these black lines are actually exactly equal to the tangent at the endpoints. There is no difference. There is no like difference between them. These black lines are the tangents. However, both of them are controlled by the same point. And you can quickly see that this actually limits the kind of curves that you can make because both of the tangents have to go to the same point, right? So if I wanted to make this curve go up at first, that forces this to go left. There is no there is no freedom to move this as I wish after fixing this. So now to fix both of these problems in one stone, i.e. the first problem being that this is not like a very versatile curve. Second problem being that I cannot control the slopes of both endpoints individually, right? I will move to the cubic Bezier curve, right? Slides not that important, but I will kind of explain what it is, right? So before what we were doing is we were using 3 times linear interpolation. We interpolated 3 points to make 2 points and 2 points to make 1 point. The same exact process is here. Between these 4 points, I linear interpolate to make 3 points. These 3 points I join. Between those, I have 2 points. And between these 2 points, I have finally 1 point. And when I play the animation, you can clearly see that this point draws a perfect cubic Bezier curve. Now, what this does is pretty insane, right? Immediately, you can see that our tangent problem is solved because now instead of controlling it with 1 point, I control it with two. You can see that these 2 points form the first tangent and these 2 points form the second tangent. What this allows me to do is, if I want this, okay, this tangent has to be straight. I can set this however the hell I want, right? If I want the tangent straight, I can do that. If I want it left like before, I can do that. In fact, I can even have it come upside down. And you can see now also that we have fixed the versatility problem, right? Because whereas here you could make, okay, wait, this curve, and then you'd have to have a whole other this thing to make the next curve, right? With just one cubic Bezier curve, we can make this entire shape. And even where there you were limited to kind of paraboloid shapes, what you can do here is you can swap these around. That actually makes a loop, which Kailash was also talking about how parametric curves allow you to make a loop, right? This is exactly how. Instead of having simple polynomial type looking functions, you can have extremely complex functions such as this, right? And I can make basically whatever kind of loop I want, right? Anyway, so that's for the cubic Bezier curve. And we have already looked at basically one numeric method to find this. But another way you can see, oh, actually, I've inverted this. But another thing you can see here is that I can still derive both of these curves simply using linear interpolation, right? The first curve was 3 times, next was 6 times. So going back to the PPT, right? Again, this offers way more control over the curve's shape and solves both the problems which we stated before, which was the second problem was that we couldn't control the slope, right? Now we can fix the slope of both endpoints exactly. But why stop at cubic? We had quadratic, we had cubic. Can't we go higher? Because obviously this curve is quite primitive, right? Again, like it's still way more flexible than quadratic, but we can't make a whole logo out of it. So what can we do? Let's try going higher. So what we can do is that I just directly went for a ninth degree Bezier curve. Now cubic curve only has 4 points, but this has 10 whole points. And right away you can see this has insane amounts of freedom. I can draw pretty virtually any shape that I want, right? And I can control it via not nine, 10 different points, two to set the endpoints, and the whole path can be defined with just these 8 points. Again, if I wanted to make such a shape with just the cubic Bezier curve, I would need to use like maybe more of them, right? And even more if we were taking just quadratic. But here we run into a few problems. First of all, you might have noticed, right? This quadratic Bezier curve only uses 3 linear interpolations. If we were looking at just a line, right, that's one linear interpolation. Going to quadratic goes 3 interpolations. We've added two more. Cubic uses 6 interpolations. We've added three more. And you might be seeing the problem here because to make such a massive curve, I use linear interpolation 45 times. And you can immediately see that if I were to use this as vector graphics, basically if I render this, your computer would, if I rendered like a really high degree curve, your computer would crash because too many operations are going on at the same time, right? If I linear interpolate 45 times just by ninth degree, imagine if I go to maybe like 20 degree, 30 degree, right? You will have hundreds upon hundreds of linear interpolations. And obviously that's a real problem, right? Second problem is, okay, fine. I have a massive versatility in terms of how I can define these curves. But a problem arises when, let's say, I want to modify this curve. Okay, this isn't exactly how I want it to look. I want it to look a certain way. Suppose I take this point, no, this point, and I start moving it around. You can see that when I move just this one point around, the effects of this moving one point is felt through the whole curve. Now, obviously, the effects are most like, how do you say, most prominent at the closest points to the curve. Like you can see here, when I move it, it's obvious like that point is moving. But smaller movements you can see goes through the whole entire curve. If you focus on that part, you can see the entire curve is actually moving when I move one point, right? And this brings us to a second thing is that this causes loss of local control. What does local control mean? It means that when I move this thing, I want to be able to control like a specified area, like a small area only should be affected by this point, right? But here, such a large curve, the whole curve is being affected by this point, even if I move it a little bit, right? This is also similar to our problem with actually making the image with polynomials, which first of all, we had a problem with loops. But second of all, suppose I wanted, okay, I'll do this via drawing. Suppose I wanted to make a curve, just a parabola, right? With polynomials. How do I select this? Yeah. This is pretty simple, right? This I would just, okay, y equals x square. Fairly simple. But the problem arises it, okay, fine. Suppose I want, okay, just a slight deformation at the bottom here, right? Instead of going down fully, I want it to come up like this, go like this. This is a pretty simple equation. But when I start doing this, right, the equation becomes a quadric. It becomes something in fourth degree polynomial, f of x, and this is of degree 4. Just for moving this, right? And that's basically a loss of local control, right? With just a polynomial, I can't have a little bit of control over small region, right? If I make a small deviation, the whole polynomial will change. And you might have also tried doing this if you have like some kind of cubic. If you change just a few numbers, right? You change one number just a little bit, you'll get a radically different curve, right? And it's really unpredictable. That's the real problem here. If I want to draw a shape, right? As an artist, I don't want to sit there figuring out exactly what formula I have to use. I want to like just do it, right? So that's like one of the major problems. So if we can't just directly increase how many, like what degree of this thing I'm using, then exactly what can I do, right? Because this is not going to cut it. Like I'm not going to be able to draw a full logo or something just via this, right? So this this is just a graphical form of what Kailash did. Yeah. This is basically pretty much according to what basically the same thing Kailash did. But I'll come. This is done purely using linear interpolation, and I will come to the formula that Kailash used in a different method. Okay, so yeah, you see, 10 points can't do much. So what we're gonna do is go to the next slide. Right. We'll continue with this like more flexibility later, right? First of all, we'll discuss, okay, fine, we have got the cubic Bezier curve, right? This is basically the standard Bezier curve because it's a good like intermediate point, right? Quadratic Bezier curves are really, really cheap, but they're like quite fixed because of the lack of degrees of freedom. Cubic Bezier curve is the first, like most earliest degree Bezier curve where you get complete freedom over the slope of the line, slope of each endpoint, right? As you go higher and higher, the computation becomes way too expensive because you have to see that LERP is really expensive in itself. I think Kailash mentioned this, and someone in chat also mentioned this earlier. If I were to zoom into this, that's basically I'm recalculating the formula to make this line. I'm actually calculating the linear interpolation formula. Suppose for a big resolution, I have to calculate this 1000 times. I will use the t by iterating t. I will use t at 0, then 0.1, then 0.02, then 0.03. Right? Like this, I will collect all the points on the curve. And using those points, I can render I can actually draw the image. Right? So making a linear interpolation is itself like decently expensive. So as we add more and more points, the number of linear interpolations that I have to do increases quadratically, right? So it becomes basically computationally infeasible to do. I hope everyone is following, right? Uh, Divit, yeah, I will come to that later. Why we need to this linear interpolation was just used to like kind of derive the curve, right? We will come to the actual formula later. So we can represent this curve. So now in computer graphics, right? I won't actually like this thing. What do you call it? Put it in Desmos and find the curve and put that in Photoshop or whatever I want to draw the curve in. Right? What I'm gonna do is basically I have to find a way to represent this curve in a computer, right? So if you've done any computer science, obviously, if you want to represent an integer, then you can just use a variable, like an integer or a string or anything, and use a variable. How do I represent this curve, right? And there's a few different ways I can do that. So a naive approach would be to directly create it from lerp, like how I used it just now. This is called the de-Castle-Jaw form, right? I just do lerp, 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 and I get the curve, right? So this would be how you would represent the cubic Bezier curve, right? You linear interpolate one, so you have the 4 points, the 2 points, and the control points. You linear interpolate, and then again and again and again and again until you get the final curve, which is this, right? Again, like I mentioned, this gets really computationally expensive, right? Each lerp requires higher and more calculations if you want higher and higher accuracy of the curve, right? So this is not that great, right? Because lerp itself is quite expensive and I want to do that 6 times. So instead of doing that, okay, can I reduce 6 calculations to 1 calculation? Now, the Kailash discussed, right? This is the actual form of the lerp, right? P1 into 1 minus t plus P2 into t. This will directly give you the lerp, right? When if t ranges from 0 to 1, this gives you the line. What we can do is, since we had all of these lerps, but we can represent a lerp via polynomials, right? Like this parametric function. What if I expand all the lerps? And that's where you get the Bernstein form. The Bernstein form is basically I expand this lerp and 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 this lerp. I simplify everything. I put it into one clean equation. These are the 2 points, first point, end point, control points, and suddenly we're back at the binomial expansion. This is what Kailash did, but now we have correctly derived this just from first principle. From the linear interpolation, we have gone through everything and we have found this form, right? How does linear interpolation make the curve? Okay, wait. Sorry. Okay. So you got the first thing that when you do linear interpolation, basically this t ranges from 0 to 1, right? As it goes from 0 to 1, so I'll open the formulas here. Um, Here. So as I'll select this, as p ranges from 0 to 1, this is p1, this is p3, and this is p2, okay, in this graph. As t ranges from 0 to 1, this point will kind of move. You can see this point will move from the first point to the first point to the control point. You can see the green X, right? Similarly, you can do with these 2 points. It starts here with t equals 0 and it ends here with t equals 1. Now, what happens in between that to draw the curve is that I have 2 points now, and I can take these 2 points, define a line, and do lerp on that line, the line between the 2 points, and the 2 points themselves are moving, right? The 2 points themselves are moving. You can see like at small t, right? These 2 points are like at the beginning, and between them there's a line. On that line, this star is at the beginning. So basically, I'm running the lerp with the same parameter on this new line which I have created, right? So when I move from 0 to 1, it goes from the first to the last, like this. Hopefully it's clear now, right? And the same process basically for the cubic Bezier curve, right? Instead of 3 points, I have 4 points. I make three green x's, which are done with linear interpolation. Yeah, the same variable t, the same variable t, exactly. Between these 3 points, I have two purple points with the same variable t, and between the two purple points, I have the final red star, which also uses the same variable t, right? So when this one t with one variable t, I'm doing the whole thing, right? Okay, we'll go back to the forms, right? Now, when I put this in a computer, already it's quite efficient, right? It doesn't use six different linear interpolations. We just need to vary this one t from 0 to 1. But when you look at actual computer processes, a computer is very good at doing addition, subtraction, that kind of stuff. That's like very, very easy. When you start getting to multiplication, that's a lot more expensive, significantly more expensive, right? When I and you when you get to division, that's like really, really, really expensive. Okay. So this Bernstein form, you can see that this reuses quite a lot of multiplications, right? And when you do exponentiation, that's when a computer does exponentiation, that basically it does multiplication multiple times. So you can see that there's a lot of different multiplications going on over here, right? This is one, right? For this, two for the times three, and then three for these. Then you got one, two, and then three more for these. Then you got one, and then three more for the t cube. And you can see that already there's a lot of multiplications. Someone can count it up in chat if you like. So suppose we want to optimize this further, we'll basically try to minimize the number of multiplications that are going on. Okay. So what I will do is, instead of doing like this, I can open all these brackets and I will basically, instead of here in this form, I've isolated P1, P2, P3, P4. So it's all neatly on the side, right? However, this time I will try grouping by power of t. So I will group coefficients of 1, then coefficients of t, t squared, t cubed, right? Now what happens is that what I can do when I actually implement this formula, right? What I can do is, if I take the pencil, suppose I have a variable, let's say x, right? When I want to do this calculation, right, of p, I will start by taking x is equal to 1. Then I will do p1 times x, right? And I will add it to here. So I will get p1. Now what I will do is I will multiply x by t. So x will now become t, right? And then I will calculate this expression. Then I will multiply that with t, right? And I will add it here for the second term, right? Then I will multiply x with t again. So this is t square. What's the purposes of this is that when I don't need to basically compute t1, t square, t cube from scratch. Instead, I'm computing one using it, computing t with one multiplication using that, just one more multiplication for t square instead of multiplying t with t again, right? For one for more and more multiplications, right? I keep t and I add t square. I multiply with t again to make t square, right? So in the end of the day, instead of having how many multiplications is this? One and then uh, two multiplications here. Totally, I will only have two multiplications. First, I will have one, then I can just directly make it t. Then I will compute t square with one multiplication. So this is plus one. Then I will compute t cubed by multiplying with t again. So plus one again. Totally, I've used only two multiplications to get all these four numbers, right? So that's a little bit about why the logic of doing this instead of the Bernstein form is. If you didn't understand that, that's fine. These are both basically equivalent. It's just that we have optimized a little bit more to reduce the number of multiplications that we are doing because multiplication is computationally expensive, right? And we want this to run fast. So I optimize the function. But actually, we can go one step further, right? This is basically the final boss, right? This form is done is basically what is used all the time, right? And that has a few, there's a few reasons why, but I'll show this. This basically combines the best parts of the Bernstein and the polynomial coefficients form. Here in the Bernstein form, we are able to see cleanly P1, P2, P3, P4, right? And then everything else is happening here. Here again, we are able to see cleanly 1 t, t square, t cubed, and then everything is happening here, right? When I do this matrix form, I can have this separate, this also separate, and I just have this matrix of numbers, right? And this is known as the characteristic matrix, right? The characteristic matrix basically contains all the properties of the Bezier curve, right? Every single property that you see defined in the Bezier curve, this is contained within these numbers in this matrix, right? And if you modify any of these numbers, you will get different types of curves, right? But that is beyond the scope of this. You can try that as an exercise. Like how Kailash showed, I think with the quadratic formula, he left out one t square and then one multiplication by two, and that gave like a completely different curve, right? Instead of the quadratic Bezier. You can do the same kind of modifications to this matrix known as the characteristic matrix, and you will get a different kind of Bezier, different kind of curve. It will not be a Bezier curve, it will be a curve, right? You can try this out by yourself at home, right? I'll show you basically how I made this. When I made all these Bezier curves, that uses the Bernstein form only. So you can see here q1 into 1 minus t cube plus 3q3 into t into 1 minus t squared, 3q4, uh, wait, here 3 t square 1 minus t, and then finally q2 t cube, right? A bit rearranged, but this basically is the Bernstein form exactly, right? And that is how I have declared this curve. And even for the ninth degree Bezier curve, that's what I did. So I made all the lines. And you can see here, right? First point, 1 minus t to the 9. Then 9, 36, all the binomial coefficients until the end. And that basically declares the curve. Right. Moving on. Now this is mostly what is used in computer graphics everywhere. And I'll tell you why. Right? This uses a matrix. And what's interesting about a matrix is I think all of you may have heard of GPU. GPU is one part that is right now extremely expensive, but this is there in every single computer, either if you have a dedicated GPU or integrated graphics that does GPU. And the entire job of a GPU is to do matrix multiplication. That is its entire job. It does nothing else but matrix multiplication. The CPU tells anytime there's some matrix multiplication, CPU tells the GPU, do this multiplication and tell me the answer. And that is the entire job of the GPU. And the GPU is extremely optimized to be really fast at matrix multiplication, right? If you were to do this like by CPU, it will be quite slow, but GPU is purpose built to do more matrix multiplication and do like hundreds, thousands of them at the same time, right? So this matrix multiplication is used so very often because you can just do this calculation in the GPU and it's very fast. Okay. Now we can move to the Bezier curve is pretty good, right? And it's very flexible, but I need to make logos or suppose that Batman logo from first. I can't make that with one Bezier curve. Nor can I make it with all such a higher degree curve because I showed you all the issues. Local control is lost and it's extremely computationally expensive. So what will I do? Let's use splines. Splines are a method of connecting multiple Bezier curves in order to create a Bezier spline. So here's some terminology. A Bezier spline is also lower triangular. Yeah. It's in order to create a Bezier spline, I connect multiple Bezier curves together. And I will do that in the next section, right? And now this Bezier spline is basically used everywhere. everything, Photoshop, even in games, like certain games, they'll have like a roller coaster creator or that kind of stuff, right? Every single place you use curves, Bezier spline is the gold standard. And I will now we'll look at some properties of the Bezier spline and how to make it, right? Before that, I'll wait 2 minutes, right? You guys can mark attendance again, and I'll go. Any doubts, you can put them in the chat. I'll go through them. Oh, in the iPod session also they did splines. Yeah, that goes to show like how universal it is. Yes, you have to mark both attendance, I think, right? Did you guys go through the derivation and all in the iPod session? Right. So now you know exactly how how the spline came about, right? And the curves also. Oh, you have it attended. Okay. Any doubts, please put. Or if it's clear, then put clear. I will wait for a little bit. Sum of all the elements in the. Yeah, actually, I'll go back to that just to show. This is 1, 0, 0. Yeah, 0. Totally, it's 1 only. All right, I think it's clear, so I'll continue. So this is a spline, right? You have the first Bezier and the second Bezier, and you have both of them connect. And with two different Beziers, you are able to make a heart, right? Which was not possible with just one. Now, a Bezier spline is basically multiple Bezier curves connected together. And when we say Bezier curves, by default, assume that I'm talking about cubic Bezier curves, right? They are connected endpoint to endpoint, right? And these are commonly used basically in every application of curves, right? Now, I'll show basically a demo over here. You can see this spline uses four cubic Bezier curves. You have one over here, you have one over here, and you have one over here, and then you have the fourth one over here, right? four different curves are connecting together to make a really complex shape that I would not have been able to do without connecting multiple Bezier. Okay. Now these have extremely useful properties, right? One problem that I forgot to mention with the high degree Bezier curve, the curve itself only passes through the first point and the last point. You might have noticed, right? Rest all points are just used to control like approximately where it goes, right? And that basically makes it quite confusing to try and like what do you call it? Create a curve, right? It's not that intuitive. However, if you see the spline here, it passes through one, two, three, four, 5 points, 5 different points. So it's very easy to control. It's quite intuitive. Second thing, you might see that each spline is completely different of the other, independent of the other. Because we saw here, right? This, if I create a cubic spline, the whole calculation is done with just these 4 points. All I'm doing here is that I'm taking 2 points, 1 point common between two adjacent splines, right? So what happens is that if I move this around, there is absolutely no movement from any of the entire curve, any other parts of the curve, right? The whole modification that comes out of this is contained within this part. That's it. There is no other movement, right? So that obviously is an extremely useful property, right? Makes it even more easier to like manipulate the curve, right? Again, you can see that it interpolates every point, and also I can every single point where it's interpolating, I can control the tangent at that point, right? This point, in fact, there are two tangents at the point because it's like at each joining point there are two different. I can control the tangent, both the entering tangent and the exiting tangent, let's say, of both curves. Like I can, this curve is kind of coming like this and going over there. I can control both of the tangents at this point. That's also quite useful. And so many different useful features we have in this spline, right? Also, when it comes to computation, right, you saw the high degree spline. Now, obviously, we're not going to use 45 different linear interpolations to compute it in real life. But when we go to the matrix form, instead of having like just a 1 by 4, four, sorry, 4 by 4 and the 4 by 1 matrix, it would become all 10th order, right? 1 by 10, 10 by 10, and again 10 by 1, which also scales quadratically. A GPU is fast, but again, this is still like really inefficient, right? To make such a massive matrix, right? So that's there, right? And but when I do this, right, I don't have quadratic scaling, right? Because only one matrix multiplication, 4 by 4 degree, is happening for each Bezier curve, right? When I add more and more Bezier curves, that's just adding one more multiplication. It's not making the multiplication way harder. Like the jump from 4 by 4 to 5 by 5 is a lot, right? Because you're adding how many elements? Nine more elements, right? Then you add 11, then you add 13, you add more and more and more elements, and it becomes way out of control, right? But when you have the Bezier spline, whenever I add another curve, that's just one more 4 by 4 multiplication. The scaling is only linear. So this is really, really cheap, and there's basically no downside to the whole thing, right? So let's look at continuity, right? Now this spline, you can see that at each joint I have two different tangent points, and I can control both of these, right? This allows us to make like pretty easily we can make a classification, right, based on how I am putting these 2 points. You can see immediately there are three types of this thing. First type of joint is this joint. This is called the broken joint, right? Because, well, literally it's broken, right? We're not that creative with coming up with names. You can see, and this is really useful in the case of you want to make a sharp turn, right? Not every logo is just, not every image is just like a very smooth, fluid curve. Like even if you look at, let's say, the Apple logo, when you look at the bite of the apple, right? That's sharp turn. So whenever you want to do a sharp turn, you will use this kind of, okay? And we'll, yeah. And these are basically not differentiable. Like if you see here, anyone who knows calculus, you guys will be familiar with the concept of continuous function, differentiable function, right? So this would be continuous but not differentiable, right? Obviously. We'll go into a little more rigorous definition later, but just for now, you guys can see that this like is not differentiable because the slope at this point is not defined, right? It's different from the left side and different from the right side, right? But it is continuous, right? Because they're perfectly linking here. This is still a closed curve, right? So that's the first type of joint. Second type of joint, this is the aligned joint, right? And you can see here, these are both basically collinear. So this point, the end point, and this control point, all three are collinear. And you can see now this produces a perfectly differentiable joint, right? Because these 2 points are the tangents, right? So you can see that slope at this point is perfectly differentiable. You get a nice smooth curve. This is pretty satisfying, right? Super smooth curve. And the final type of joint, right? This would be a differentiable, right? In the traditional sense, right? There is the no sharp turns. And the final type of joint is mirrored joint, where this exactly bisects the line between these 2 points. You can see that this is like 3 squares up and right, and this is 3 squares down left. This basically bisects. And this also is differentiable, but there's a subtle difference here, a very subtle difference here that we will discuss later. But for now, you can see that this is like perfectly smooth curve. If I have the stars that come here, you can see that they go through very smoothly. It's laggy for some reason. You can see that the star travels along this spline very easily. And all I'm doing here is basically just doing the whatever star thing I did before for all four of them, right? Little bit of magic happening to link all of them together. But essentially, you just have the star following t. You're using the calculation by following whatever t value is given, and then you do the calculation and find the location of the star. Hopefully, that's understandable. All right, that's pretty straightforward. Let's move into some more properties of this, some more rigorous definitions of what the each joint does specifically, right? Now, the three different types of joints are there. The first joint, which the sharp turn was, is called C0 continuous. C0 basically means that, okay, fine, the curves are joined together. Like there is no opening in between them, there's no gap. They're perfectly joined. That's it. There's no other specialty, right? There is like the purpose of this joint is to produce any kind of like sharp corner, right? And again, as I mentioned, this is the same as your usual definition of continuity. The second and third joints, both of them we saw produce differentiable curves, but there's a very, very, very small, subtle difference between them, right? The slope doesn't change sharply, which produce smooth curves, right? What's the difference? The difference is very, very subtle. If I play this animation here, take a look closely at these two joints. If you look at this joint, the star perfectly goes through both points. I think star is traveling smoothly and it goes perfectly. But if you look at this one, there's a sudden jump in velocity in this star. When I look at the aligned joint in this star, when it goes through this point, suddenly the velocity jumps. If I zoom out, it's a little more, a little less laggy. you can see that the star suddenly jumps in velocity when I pass through here. Hopefully that's visible to everyone. If someone can confirm, that will be nice. Um, yeah. So that is basically the difference between the aligned and the mirror joint. And we'll look at this as a mathematical definition, right? The third joint is C1 continuous, meaning it is continuous in velocity. Okay. Why this sharp jump in velocity is happening is that the curve itself is dictated by X and Y, but the star traveling along the curve is dictated by um, the speed of t. So as t has constant velocity, if the star is jumping in velocity, then you can say that it is not differentiable in t, right? The second joint, it is not differentiable in t, but the third joint is. Both of them are differentiable in x and y. Like when you look at it, right, it's a smooth curve. But when you play the animation, right, it is not differentiable in t, which causes a sharp jump in velocity. Okay, if that is understandable to everyone. Hopefully that's understandable to everyone. So when you have differentiability in t, the third joint becomes C1 continuous, C1, right? So it is continuous in velocity. But the second one is called G1 continuous, G for geometric. Geometrically, it is continuous just in X and Y. Like when you look at it, there's no difference. Like if I'm not like considering some velocity. So suppose the applications would be different. If I were using like Bezier curves to define, let's say, like some kind of roller coaster or something like that, right? Then I would start looking for C1 continuity, right? Because if the roller coaster suddenly changes velocity from like, let's say 5 meters per second to like 20 meters per second, that looks really bad, right? However, if I'm just making logos, like suppose I'm making Apple logo or Batman or something, right? Then it doesn't matter to me. Like nothing's traveling along the thing, right? So then it's like just okay, fine. G1 and C1 are functionally equivalent, right? That doesn't matter at all to me. Okay. So I think hopefully it is clear that the difference between C1 and G1 continuity, right? So now we'll derive that. Okay. So we saw that aligned joint doesn't produce C1 continuity, but mirror joint specifically produces C1 continuity. Why is that? We'll go through a little bit of derivation, like short derivation, and we'll see how a mirror joint produces C1 continuity, right? For this, I will be using the polynomial coefficients form, right? And what I will do here is, suppose I have two different curves uh, here. I have curve A, and this has, let's say, that's not really a cubic Bezier curve, but like suppose, right? And this has, let's say, control points like this, right? These are the two control points. And this is curve A, right? And I'll change the color here. This color, I guess. And another curve B, let's say it looks like this, right? And this has again two more control points like this and like this. This is curve B. And what I want is C1 continuity at this specific joint, like right here. Okay, that's what I am looking for. So how do I produce this behavior? What I will do is, so now we saw that changing t as you vary t from 0 to 1, it travels along the curve, right? We can see the animation, but otherwise how would we mathematically know that a function is differentiable in t or not? That's yeah. Hmm. So basically, like to calculate the velocity, like mathematically, if you want to calculate the velocity, you can see here P defines the point, right? This kind of leads into this derivation. P kind of defines the point, right? As it travels, as I plug in T from 0 to 1, P travels from here across the curve, right? When if I want to find the velocity of P, I can differentiate. Simply if I differentiate by T, right? Or dP by dt here. Probably should have written that. Dt equals this. So I differentiate 1, it becomes 0. T is 1, t square is 2t, and t cube becomes 3t square. And basically the rest of it is left like that, which is why I chose the polynomial coefficients form firstly to demonstrate this. Right? Now, if I want to measure differentiability, basically I want to measure the velocity at the end of A. At the end of A means there is a difference in effective length of the curve, so it appears fast. I mean, you can kind of understand it like that, but like it's trying to explain it is not trying to explain how aligned this thing produces different velocities is a little unintuitive. You can see basically that this at this point, when I approach from the left, right, velocity at the point would be a prime at 1, but it's also b prime at 0. On this side, it's b prime at 0, right? Because at the end of curve A, t is equal to 1, but at the start of curve B, t is equal to 0, right? Hopefully that's understandable. Yeah, t is 1 at the end of A, right? And b is 0 at the end of t is 0 at the start of B. So you guys can kind of see now, okay, so if I want C1 continuity, this velocity should be equal, right? So Chaitanya activities, yeah. So basically, if it was just G1, basically these two would not be equal. But since I want C1, I will set them equal, right? And what I will do now is basically I will plug in this directly. I will plug in this. I will substitute T is 1 here for the LHS, and for the RHS, I will substitute T is 0, right? And instead of P1, P2, P3, P4, I'll use A1, A2, A3, A4, or B1, B2, B3, B4, right? So basically, I will define this as A1, A1, and this as A2, this as A3. This is both A4 and B1 because when you make the spline, obviously endpoints are connected, right? Both of them are common point. A4, B1, this is B2, this is B3, I'm sorry, and this is B4. Why does that look like D? Okay, B4. Yeah. So now I will plug in this equation directly and I will equate both sides. And what happens is that when I substitute the proper values of t, I get LHS is equal to minus 3a3 plus 3a4 minus 3b1 plus 3b2. Then obviously, as I mentioned, this point is common. This point is common. So I will change b1 to a4 and I can just cancel all the threes. I get this equation. And with a little bit of jugglery, I can see that a4 is the midpoint of A3 and B2, right? I take this side, I take this side, and I take 2 on the other side. A4 is A3 plus B2 by 2. So I take this point, midpoint of these 2 points is equal to A4. And that basically defines how C1 continuity basically leads to the mirrored joint, right? Everyone got it? I'll pause for a little bit to take doubts, because this is a little bit confusing part. Hopefully, everyone's following along. Got it. Wonderful. All right. Then we'll move on. Yeah. I'll give it to Kailash now, and he will instead of actually looking at just pure math, we'll look at actual applications of the spline, right? So we look at some actual drawings, which is using the Bezier spline in Desmos. Kailash, over to you.
Okay, hello guys, can you hear me? Uh, Hopefully I'm audible. Can somebody like put yes or something if you can hear me? Okay, cool, nice. Okay, so yeah, let's do this Apple logo thing. But before that, I just want to talk quickly about this continuity, like a different perspective of for continuity. So let me just draw a cubic Bezier here. So it is, as Arav was saying, it is just a binomial expansion, right? And we also discussed that some time ago. So let me just do that. Um, and then 3t squared 1 minus t. And lastly, we have, no, this is wrong, right? This should be squared. Yeah. And then it's s 1 minus t. Sure. The circles code is light for now. Don't worry about that. That is just some pseudocode which uh, basically in that. Okay, let me just go to that. Like slight tangent. I'll go to that part and then I'll come back. See, basically what this thing is saying is if image got bigger, didn't get bigger, so got larger is false, then you don't have to do anything. If got larger is true, then it will come to this second line and then it will return the image with a finer grid. But then how do we do the finer grid? We don't know. For that only we created parametric functions. So hopefully that's clear. If it's not, we'll talk about it after the session. But anyway, so basically this is the cubic Bezier, right? And let me put this tangent here. So uh, okay, this is between P and R, I suppose. Wait 1 second. Um, have I done this right? Oh, this is squared. Oops. Okay, that should be cube. Okay, now it should be fine. Yeah, it's not real code. Okay, so polygon from P to Q. Yeah, so basically the point is if you look at this control line, it is basically tangent to this thing, right? And a velocity is basically the tangent direction. Similarly, if I do it for the other side, if I join R and S, you can again see this is a tangent to the curve at this point, right? So when you join two cubics together, what G1 continuity is saying is that this tangent should be parallel to the next tangent. That's all G1 continuity is saying. It's not talking about the magnitude of that tangent. It is simply saying that they should be parallel. C1 continuity is saying that the tangent should be parallel and they should be equal in length. So, oh, also this is cubed. Yeah, correct. So yeah, hopefully this is clear now. The difference between C1 and G1 continuity. G1 is just making the tangents parallel. C1 is even setting their magnitudes to be equal. So that's why the other C1 has to be a mirror image. It has to be uh, at the midpoint. So yeah, that's the basic difference. Okay, so now hopefully everything so far is clear. And so let's do something pretty exciting, which is I spent like 1.5 hours drawing this Apple logo using curves. And like uh, these are all a bunch of equations, as you can see over here. All of them are cubic Bezier curves to get the entire Apple logo. So this is actually how the logo was drawn in the first place. So if you remember to the very start of this whole session, we were talking about how we want images to be nicely scalable. So think about a company logo, right? You want to put it on the website, you might put the company logo maybe in a presentation or something. And in all of these things, the logo will be in different sizes. And you don't want to make a 4K logo and put it on your website. Your website will crash. You can't put a 4K logo. So what they instead do is they use these kind of splinings to and store these equations instead. And so let me demonstrate how this thing now will have nice scaling properties. So let me go come back here. So the slider, as you can see over here, is saying s is equal to 1 right now. So let me maybe make this a bit bigger. Yeah, so this is s is equal to 1 right now. And as I increase this, you can see that it perfectly scales. So let me like zoom out nicely so you can scale it. So I'll increase this. Yeah. So it's perfectly scaling. It's becoming exactly what it like the proportions are staying as it's supposed to be. Everything is not it's not like twisting and turning in any way. And most importantly, it's not getting blurred at all. And I mean, now that you've seen all these equations and stuff, it's probably very obvious to you. Like, yeah, I mean, obviously, it's just a math equation. Why will it get blurred? That's the whole genius of it, right? To like not even use pixels anymore and to use math equations. So let's like make it up to 20. So this is 20 times the original size. Okay. So when have you ever made something 20 times bigger than its original size? Probably never. But that shows the power of these splinings and Beziers and stuff. It holds its shape so well. And the next thing which we can do is this black point in the middle is basically showing the about the center of mass of this thing. It's not exactly the center of mass, but approximately. And if I move this around, everything moves around perfectly the way it should. And that comes because of the translational equality, whatever the technical term is, I don't know. But if you do a translation, it won't distort, right? We derive that with equations on paper. So you can see how the logo is like moving exactly the way it's supposed to move and stuff. Uh, right, so that is a pretty nice feature. Let me bring this back to one scale. Yeah, that's how small it's supposed to be. Like, yeah, 20 times it's, I mean, I know that's supposed to be like this, but every time I see it, it's cool. So yeah, let's bring it back to normal. Okay, now let's just inspect the curve a little bit. Let's look at all the points I've used. So hopefully you guys can see the points here. And let me actually highlight this. So you can see all the points here. And I'll also highlight the tangents. So yeah, let's zoom in nicely. Okay. So let's maybe start here. So this is one Bezier curve. Can you guys see this is a purple point? This is the other purple point. So these are, sorry. Yeah, purple is the end point. So this is the start and this is the end. And then we have two control points which are in blue. Okay, this is supposed to be in blue. I forgot to change the color. That's my bad. But yeah, so you can see this is one cubic curve. And this is a point where we are starting another cubic curve. So this is basically a spline, right? We are joining two cubics together. This is the point where that happens. And this is basically a point where you have C1 continuity, sorry, C0 continuity, right? And if you look at the leaf over here, this is an example of no continuity. It's discontinuous. It's just cooked. There's nothing going on there. And so this is another cubic curve. And this is the kind of stuff you cannot get by doing y is equal to f of x. So that's the whole power of parametric functions. Can you see if I do this vertical line test thingy, there are 2 points with the same x coordinate but different y values. That's just not possible if you're using y equal to f of x and plotting the x and y coordinates. So right, so that gives the bite of the apple nicely. Again, these are the two control points. And this is another example of C0 continuity. Now this is interesting. If you come down here, you can see these two fellows are mirrored, right? So these are mirrored, and I've done that right here. You can see P11 is 2P10 minus P9. That's how we calculate midpoints, right? Even in G. So this is now a point where it's, and now you can see it's like exactly smooth and stuff. So this is a C1 continuity, and this is one cubic curve all the way here. This is again a C1 continuity, and so on and so forth. This is again C1 continuity, blah 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 blah. And totally, I've used how many? I've used 8 different cubics to make the apple, and I used 2 cubics to make the leaf. So that makes the Apple logo with just Bezier curves. There's no pixels. I mean, there are pixels obviously, but the instruction set is not the pixel values. It is the curves. which is brings us back to the start of the lecture, right? So yeah, let me just save this and just let's look at the Batman logo as well. So this is the Batman logo I like botched up in about 5 minutes to show you guys what you can do with Beziers. Here we're using both cubics and there's also a linear interpolation which I used in order to draw this. So that is a lerp. So where have I done that? Yeah. So you can see right here, this is a linear interpolation and these are all cubics. And again, you can see this is a C0 continuity. But here there are actually two cubics. I've hidden all the points, so you can't see it. But basically, this is one cubic till about here. And then this is another cubic. So here there is a C1 continuity. And I guess the shot of shows the beauty of C1 continuity. Like you can't even see that there is a thing here. That's how smooth it is. So, okay, my OCD is hurting. I didn't align this properly. Uh, can I do that? Wait. Uh, where is that point? Yeah, okay, I don't know. I'll fix that later. But because I have to search that point here, I don't remember my indexing scheme. But yeah, so basically this is how I made the Batman logo. And here also I very like slightly turned the ear to point this way. And the way I did that was using these control points. So let me highlight these control points. So you can see if I just move this like this, only this part of the logo gets cooked. This does not look like a ear anymore. But then every other part of the logo is perfectly fine. So this is what Ara was talking about, that splines give you local control, which you didn't get with the with using a high degree Bezier curve. And if I want the ear to point way to the left, I can do something like this. Okay, that now does not look like a ear anymore. Yeah, so maybe something like this, right? So now it points nicely to the left side. So yeah, you can do all sorts of things like this. And yeah, so that sort of concludes this session, I guess. So just to recap, we started off by talking about uh, drawing something. I mean, how can you make a computer store something which scales nicely while making sure you don't cook your file size? One solution, obvious solution, is to use 8K images for everything. That will just destroy your file size thing. Your entire SSD will be filled with font size only. So we talked about this in the start. And then we were like, okay, we can use functions to draw stuff. We can give an instruction set to the computer by using an y equal to f of x. But the problem with y is equal to f of x is that you can't loop like how we are looping here. So you can see a better example would be the Apple logo, where the byte of the apple for the same point, for the same x value, we had two y values, right? You cannot achieve this with y is equal to f of x. So motivated by this, we stopped using y is equal to f of x and then we switched to a parametric function. So that was that part. And then after that, we formalized the idea by talking about lerping and recursive lerping, which led us to Bezier curves. And then we talked about splining, which is joining different Bezier curves together. And lastly, we talked about different continuity and classes of continuity, which sort of brings us to this last part of the lecture with this logo and all these things. So yeah, so that concludes this thing. Hopefully you guys liked it and enjoyed it and stuff. Yeah, if you guys have any questions, we can talk about it. Okay, so I was just curious about how SVG converters work. Um, if you mean by an SVG converter, if you mean you enter some PNG or JPEG and then it returns an SVG, it internally basically what it does is it will find these edges in your vector graphic, like not vector graphic. Let's say you input this Batman logo, but you input it as a PNG or as a JPEG. Uh, then what that SVG converter would do is it will try to find edges, and the way it will find an edge is by using maybe some kind of matrix. And what that will do is it will look at where is the pixel value changing. So here you can see, okay, as I'm zooming in, it's not becoming blurred. So I can't show you guys this thing, the pixel itself. That's the beauty of a Bezier curve. But you guys can imagine how there's a pixel here which will be black, and there's a pixel maybe to the top left here which will be white. So you can have a something that looks at where does the pixel value change. So this is at 0 and then it's now at 1. So that's an edge, right? So it will nicely go and find all the edges in your thing. And by using this idea of a Bezier curve and interpolation, it will figure out what equation draws that line. So that's how SVG converters work under the hood. Now, if you think about how exactly does it go and find these edges, how does it work so well? Lot of complicated, crazy math goes behind the scenes. Um, you guys can, there's a 3B 1B video about convolutions. So that video nicely explains how edges are detected in pictures. So if you're very interested, I would recommend you go and check that out. So that would be pretty an interesting watch if you're interested in these things. So yeah, that's briefly how SVG converters work. So yeah, are there any other questions? By the way, if you have asked something and I'm not replying immediately, it's because there's a chat lag. But yeah, so I guess there are no more doubts, right? So I guess we'll wrap right now. As a fun exercise, I would encourage you all to try and draw this Batman logo yourselves. Yeah, exactly. Like Arav put in the chat, you can try and make this using Beziers. You can. So in one slide, I drew a heart, right? So let me show that slide. Uh, yeah. So you can try and draw this using a Desmos. I drew this with Desmos. This is a screenshot of a Desmos thing, and I erased the background. So yeah, you guys can try doing all these things. It'll be quite fun. We will send an assignment as well, which will also involve a lot of Desmos graphing and stuff. So yeah, hopefully you guys had fun. And if you have doubts, you can send us in WhatsApp and we'll chat. So yeah, so I'll end the stream here. So thank you all for coming and bye bye.